Hi everybody, in this video we're going to take a look at mirror symmetry. It is designated by the letter M when you look at crystallographic symbols. So the letter M means that a crystal has one or more mirror planes. And we're going to use this very nice diagram from Dexter Perkins in his online textbook in mineralogy to illustrate. So he shows here a butterfly and there is a vertical mirror plane. You notice that everything on this left hand side of the butterfly contains all the information we need. If we take this left hand side of the butterfly and combine it with this mirror plane, we can now create this right hand side of the butterfly. So that's what a mirror symmetry mirror plane does. It allows us to take information and then repeat it, but repeat it in a certain way. Notice that what's shown over here is not exactly the same. If we took these two leaves of the butterfly's wings over here and overlaid it, they would not, of course, match exactly what we see. This is not a translation or rotation kind of symmetry. It's a special new kind of symmetry where, again, we create what should be a relatively familiar concept of a mirror image. Over here, we have the same kind of thing, another vertical mirror plane. We have some information over here, a hand. It looks to be a right hand. And when we project it across this mirror plane here, then we get this mirror image. Notice that we've changed the handedness. So we've got a right hand over here and a left hand over here. So we've recreated that information, but we've changed the handedness. And when we do that, when an object has an intrinsic handedness, then we call it an enantiomorphic pair. So we'll just write that down here. Enantiomorphic, let's see if we can spell it correctly. So an enantiomorphic pair is when you have something like this case here, when the image has some distinct kind of handedness. That's not really the case here or in these other examples that we'll look at on the right-hand side. But when you have distinct handedness for, well, a hand in this case, or a set of atoms for a particular crystal, then we would create an enantiomorphic pair where the left-handedness would turn into right-handedness in the reflected object. How about over here in letter D, the blob? There are no lines we can draw here. There's nothing we can draw where this side would be the mirror image of the other side, no matter how we draw it. So there are 0 mirrors here. So we could say that the mirrors are equal to 0. The circle is kind of an interesting case. So there's a mirror plane drawn here, and you can see that this side is the mirror image of that side. But notice that we could have drawn a mirror plane here or a mirror plane here. Any line that goes through the center would count as a mirror plane. We'd just be dividing the circle into different places, but we'd still get if we drew a mirror plane here, we'd still have a half a circle here. It would be the mirror image of the other half of the circle here. So how many mirror planes could we draw? You might want to pause the video here to think about it. Well, the answer is we could draw an infinite number of mirror planes for a circle. So a circle really has an infinite level of symmetry. How about the rectangle here? We have a vertical plane and a horizontal plane here. So we have 2 mirror planes. Notice that we cannot draw something through the corners. Well, we can draw a line, but it's not a mirror plane. If we try to assume a mirror plane is here and look at how this corner would reflect, it would reflect across that mirror plane, but there's no corner. We don't reproduce that corner there. And similarly, if we take that corner and reflect it across the mirror plane, we don't reproduce that corner over here. So this is not a mirror plane. The number of mirrors in that rectangle is merely 2. Let's take a look at the square. You can pause the video again if you want to try to count up the mirrors ahead of time. They are all drawn for you. Not all of these lines are independent. Notice that in this vertical plane, we have a mirror plane here, but that's the same as this fellow that's down here. That's one mirror plane. There's a second that goes through the corners. This is a perfect square, so this corner will reflect across that across this mirror plane over here to get that corner. So that's a third mirror plane here. This one here is taking this corner and reflecting it to get that one. And then we have a 4th mirror plane that's horizontal. Yeah, we don't have to necessarily number them in that order, but for the case of the square, the number of mirrors is equal to 4. If you got 3, well, I'll have to admit the first time I recorded this, I miscounted and got 3 as well because I forgot this guy down here. I just counted 1, 2, and 3 for the vertical, horizontal, and that first diagonal. But we have 2 diagonals. diagonals. Notice that we can't continue counting 5, 6, 7 because those are really just extensions of the 1, 2, 3, 4 that I've already drawn. Over here, the cube gets much more complex, so we take a square and add this third dimension so that we create a cube. We have a number of mirrors here, so there's one that is vertical, and that's shown there, and then another vertical one that goes north-south that would be drawn there, and then another another horizontal fellow that goes there. So there's 3 mirrors that are shown there. And then there are mirrors that cut through the corners and the diagonals through the edges that create a larger number of mirrors, than many more than what we would just get in the two-dimensional square here. We won't give away the total number of mirrors because this might be an exercise that your teacher in crystallography or mineralogy might want you to solve. So there we go with mirrors. In a couple of other videos, we talk about how we could take the same concept and apply it to collections of atoms inside of a crystal to talk about mirror symmetry, taking numbers of atoms and then recreating those atoms to create patterns.